Hello everybody, welcome to video number 21, radiometric correction in ENVI. So recall we're working on a Landsat image. Our ultimate goal is to try some spectral mixing. In the last video I showed you how to use dark object subtraction to estimate path radiance and remove it from our image by subtracting the value of the darkest pixel in the image. So in this video I want to show you how to make a radiometric correction. So I'll start out by talking about what a radiometric correction is and why is it necessary. Then I'll show you where to find the relevant information, and then I'll show you how to make the correction in ENVI. So recall that a spectral reflectance curve is what's often used to identify different materials on Earth's surface. This is a plot of the percent of light reflected in any given wavelength, and it's different for each material. So each material basically has a barcode. And of course, these are determined by going out in the field with a handheld instrument. But the problem is that the satellite doesn't measure reflectance directly. It measures radiance, the amount of light arriving at the sensor. So in order to compare with spectral reflectance curves measured in the field, we'll need to do a couple of different things as part of this radiometric correction. So first, a quick review on how radiance at the sensor is derived. The sun beams out a radiant flux in watts. Some of those watts reach ground as an incident irradiance, or E. That's in watts per meter squared. Some fraction of that light is reflected, and that fraction is given by the reflectivity or reflectance rho, a unitless number. And then the amount of light leaving the surface is given by the outgoing radiance, L, which is simply equal to the reflectance times the irradiance times the fraction of energy that makes it through the atmosphere, that's the transmissivity, and divided by 2 pi to correct for the hemispheric geometry. So that outgoing radiance is measured at the sensor, but it's combined with the path radiance, which is reflected off the atmosphere. So in the last video, I showed you how to subtract away this path radiance and actually compute L directly. So in this video, I want to show you how we can use L to actually calculate reflectance. So we can now recognize that reflectance is just given by the ratio of outgoing radiance over irradiance. So to estimate that reflectance value, the first thing we need to do is convert digital numbers in the image back to outgoing radiance using a radiometric calibration. Then once we have that outgoing radiance number, we need to estimate the incident irradiance to complete the ratio. So to convert digital numbers to radiance, recall that we'll just use the radiometric response function, which relates any digital number in the image to the spectral radiance or radiance that was actually measured by the sensor. For Landsat and other sensors, this is a linear relationship with known parameters. Estimating the irradiance on the surface is a little more complicated, and we need to consider 2 different things. The first is the solar angle. When the sun is shining obliquely to the surface, the energy density is lower on any meter squared patch of ground, and the reduction in energy density goes as a cosine of the solar angle. So the irradiance on any meter squared is given by some reference irradiance, what it would be if the sun was vertically overhead, times cosine of the solar angle, where the solar angle is measured relative to the vertical. The second correction is for the Earth-Sun distance. When the Earth is farther away, slightly less energy makes it to Earth. When it's closer, more energy makes it to Earth. So the amount of energy reaching Earth falls off as 1 over Earth-Sun distance squared, so 1 over d squared. Again, the incident irradiance on a patch of ground is given by the reference irradiance, if Earth was 1 AU from the sun, divided by d squared, where d is in astronomical units. So if we combine those 2 equations, we get the combined irradiance estimate, E equals E naught times cosine theta over d squared. And that's the equation that ENVI will be using. So in summary, our goal is to compute reflectivity at the surface, and to do that, in the last video, we started out by subtracting path radiance to estimate outgoing radiance, L. Then, what we're going to do now, the first step, is to convert the digital numbers to radiance using the radiometric response function. Then ENVI will estimate the incident irradiance using the equations we just went through. And once we have L and E, we'll take their ratio to get the reflectance. So before we go to ENVI, we need to know where to get some of this information. For example, solar angle or Earth-Sun distance. And that information is going to be found in the metadata. So navigate back to your folder and find your original Landsat image in the folder. And in there you should find a file that ends in .met. And that's the metadata file. I've already gone ahead and added a text extension, so I can just open this right away in WordPad. Now grab a pencil and jot down these 6 variables that we're about to record out of the metadata. The first variable is the spacecraft ID. That's Landsat 7. The second variable is sensor ID. That's the Enhanced Thematic Mapper sensor. Then we'll need the acquisition date, July 21st, 1999. And then we'll scroll down a little bit and get the solar elevation angle, 59.669. And then down a little bit more and get L max. That's the maximum radiance that the sensor measured, and L min, the minimum radiance that the sensor measured. And those values are specific to band 1. So that's 191.6 and minus 6.2. So if you've got that info written down, you're ready to head into ENVI and make the radiometric correction. So here in ENVI, I've got my project open. Notice that I did a dark object subtraction for all 8 Landsat bands. So they've all been corrected for path radiance. And to do the radiometric correction, we'll go back to the toolbar under radiometric correction, and I'll go down and find Calibrate Landsat. Why don't we do this first on band 1? So here I'll enter the satellite and sensor, but it's already set to that because ENVI knows what it is when it imported it. But I do need to update the date, July 21st, 1999, and the sun elevation, 59.661. I'm going to leave this set to band 1, and I have the option of computing radiance or computing reflectance. If I compute radiance, it's only going to go through the first part of the correction, in which it converts dN to radiance. If I choose reflectance, it's going to go through the whole thing, including estimating that irradiance value and taking the ratio. Okay, so I want to do reflectance. Now I'm going to double check. ENVI already knows L min is minus 6.2, L max is 191.6, so I don't need to adjust those. And I'll save this back in my folder, and I'll give it a name, B1 clip ref, and that is for reflectance. Hit open, hit OK, quick calculation, and I've now got a calibrated reflectance image rather than a digital number or radiance image. Just to verify that worked, I'll grab the cursor value tool, look at some of these dark areas, and I'm getting reflectance values here of pretty low, 0.02, so that's 2% reflectance. Over here in the brighter area, I'm getting as much as 0.2 or 0.3, so up to 30% reflectance. That sounds about right. So in summary, you've learned why a radiometric correction is necessary to compute reflectance. You learned how to find the relevant information in the metadata, and you learned how to make the radiometric correction in ENVI. So please join us for our next video, where I'll show you how to extract a spectral end member using a region of interest in ENVI. Thanks.